Welcome. Let's take a look at evaluating the derivative of an integral where both limits of integration are defined by variables. Before we dig into this, I do want to remind us about the second part of the Fundamental Theorem of Calculus. So down here, if we have a function defined as an integral, and notice that this lower limit of integration is constant, and this upper limit of integration is a variable. If we have a function like that, then the derivative of that function can be found by simply substituting in the variable x for the integrand, for the variable in the integrand. In this case, in the theorem down here, we're substituting the x for the variable t. So let's take a look how this applies to the example we have here. We have the derivative with respect to x of the integral from x to x squared of t squared times cosine of t dt. Now, keep in mind that our function, our little f of x, this t squared cosine of t, that function must be continuous on the interval defined by our limits of integration. So this should be continuous on the interval from x to x squared. Well, the product of t squared and cosine of t, a polynomial times the cosine function, is continuous everywhere. So it doesn't matter what x is, this function will be continuous on the interval from x to x squared. So we've verified that our function is in fact continuous on the interval represented by the limits of integration. So now we look at those limits themselves in terms of being able to find the derivative of the integral. And the first thing I notice is that my lower limit of integration is not a constant as prescribed by the theorem. So we need to do something about that. Now, since our function here, our integrand is continuous for all real numbers, what we can do is we can use the addition property for integrals, and we can rewrite our integral like this. The derivative with respect to x of the integral from, and I'm going to pick an arbitrary constant. I'm going to choose 0, from 0 to x squared of t squared times cosine of t dt plus the integral from x to 0 t squared cosine of t dt. Now, remember that property of definite integrals. When you're adding two definite integrals and the integrands are identical, and the lower limit for one matches the upper limit for the second, remember that these can combine to become the integral from x to x squared, t squared cosine of t dt, which is the function that we want to take our derivative of. Next, we'll use the idea that the derivative of a sum is the sum of the derivatives. That means I can rewrite this as the derivative with respect to x of the integral from 0 to x squared, t squared cosine of t dt, plus the derivative with respect to x of the integral from x to 0, t squared cosine of t dt. Now notice that this first integral that we want to take the derivative of basically matches the structure that we have here. The second integral we want to take the derivative of does not yet match that structure. Fortunately, that's pretty easy to fix by reversing the order of integration. So we'll have the derivative with respect to x of the integral from 0 to x squared of t squared cosine of t dt plus the derivative with respect to x. Now I'm going to reverse the order of integration there. So I'm going to get a negative integral from 0 to x of t squared cosine of t dt. Now, just to be a little clearer, I'm going to rewrite this one more time and pull that negative from the second integral out and turn that addition into subtraction. Equals the derivative with respect to x, the integral from 0 to x squared, t squared, cosine of t dt, and pulling that negative out in front and turning the addition to subtraction. Derivative with respect to t of the integral from 0 to x, t squared cosine of t dt. Now, at this point, both functions here that we're trying to take the derivative of are of the appropriate structure. One thing to note, though, is that when we do the derivative for this first integral, I have a function of x squared, as that upper limit. So when I take the derivative, I'll need to remember to use the chain rule. And so you might be wondering what the inside or the argument of this function is, and that is this upper limit of integration. So let's take a look. So if we're applying the Fundamental Theorem of Calculus, we would go ahead and substitute in that upper limit of integration for the variable in our integrand. So we would have something like x squared cosine of x squared. I've done that substitution, but because my upper limit of integration is not the single variable x, but a function of x, we need to multiply by its derivative. So that first term is going to end up being x to the fourth times cosine of x squared times 2x. Now, focusing our attention on this second term, notice that this particular function does match the structure that we have down here in the Fundamental Theorem of Calculus here. So we can directly substitute this upper limit variable x into t in our integrand. So this is going to look like x squared, substituting in the x times cosine of t. So this would be, cosine of x. This would be x squared times cosine of x. Simplifying a little bit more, in this first term, we'd have 2x to the fifth cosine of x squared minus x squared cosine of x. So that would be the derivative of our integral here. Now, let's look at a second example. In this case, we are looking at the derivative of the integral from x to natural log of x, e to the t dt. Now, keep in mind that our integrand, this function right here, is continuous on any interval. The exponential function e to the t is continuous everywhere. So that part is good. What we do need to notice, though, is that one of our limits of integration is the natural log of x. So that's going to limit the values for which we can evaluate or substitute in for x. So recall that the natural log of x, its domain is x is greater than 0. So this function here is only defined for x greater than 0, not equal to, just strictly greater than. So we can use the strategy we used before to separate this function that has an upper limit with a variable and a lower limit of a variable by choosing an arbitrary value constant to split the integral at. In this case, I cannot use 0 because my upper limit of integration is not defined at 0. I could use 1. 1's a perfectly good option, and both the upper limit and the lower limit, as well as the integrand, are defined and continuous at 1. So that's a good thing. So what we'll do here is we will rewrite this as the derivative with respect to x of the integral from 1 to the natural log of x, e to the t dt plus the integral from x to 1, e to the t dt. Now I just want to remind you again, we're taking advantage of that property of definite integrals that says when your lower limit of one integral matches the upper limit of the other and they have the same integrand, both conditions must be satisfied, then we can simply this is the same as the integral from x to the natural log of x, e to the t dt, which is the original function we're trying to find the derivative of. Now, having split that integral into two parts at a convenient constant value of 1, we will go ahead and switch the limits of integration for the second integral so that the fundamental theorem of calculus can be applied. So this will end up looking like the derivative with respect to x of the integral from 1 to natural log of x, e to the t dt, minus the integral from 1 to x, e to the t dt. Now in the previous example, I used the property that the derivative of a sum was the sum of the derivatives. In this case, I'm going to use the property that the derivative of a difference, or the derivative of subtraction, is the difference of the two derivatives. In other words, we're going to have the derivative with respect to x of the integral from 1 to natural log of x, e to the t dt, minus derivative with respect to x, the integral from 1 to x, e to the t dt. At this point, we can start applying the fundamental theorem of calculus. That upper limit of integration gets substituted into the integrand, and we have to watch for occurrences of the chain rule. So for example, this first term, we're going to go ahead and substitute in the natural log of x for t. But since that upper limit of integration was not x alone, but a function of x, we will need to multiply by the derivative. of the natural log of x minus, for my second term here, this derivative, my upper limit of integration is a constant. Is x. My lower limit of integration is a constant. It's perfect for applying this Fundamental Theorem of Calculus. And we simply get e to the x. Continuing on, we have e to the ln of x. We'll think about what to do there in a moment. Times, now my derivative of ln of x is 1 over x minus e to the x. Now, there's just a little bit more we can do. You need to recognize that e, the exponential function base e, and the natural log function are inverse functions. And so when you compose inverse functions like we have here, you simply get they counteract each other, and we get simply just x. So we have x times 1 over x minus e to the x. And x times 1 over x is just going to simplify to 1 e to the x, or minus e to the x. Now keep in mind that way back in the beginning we identified that the domain had to be x greater than 0 for this integral, this function, to be defined. I hope you find this helpful.